All right, good morning, everybody. It's thermodynamics time. So this is um, one of four more lectures that we have left to go here for thermodynamics through 331 this semester. The time has just gone by really fast. I've given almost about, I think this is the 20th video lecture I've given for the class. It seems like we haven't covered enough material, but I'm going to do the best I can today, and I'm going to cover some gas power cycles today. Right now, as I give this lecture, it's Sunday afternoon, and I'm getting some questions about the homework. Um, so I will be addressing those shortly after I give this lecture. So hopefully people do okay with the homework. It looks like it might be a little labor intensive. I'm sorry about that. But one way you'll really remember how to do Rankine cycle if you practice it and have to do it over and over and over again. But I will check to make sure that it's not too much work. Okay, so let's go on here. First thing as usual is we look at the results from the survey from the last class from lecture 36. So what is one way not to increase the thermal efficiency of the ideal Rankine cycle? Okay, so we talked about the different ways to improve the efficiency of the Rankine cycle. Decreasing the condenser pressure is actually one way to increase the thermal efficiency of it. So I don't know where people got this idea, but that is if you decrease the pressure of the condenser, you drop it below atmospheric pressure, for example, you're going to get higher efficiency. So that's the reason why they do that. Okay, increase the boiler pressure. No, it's a way to increase increase the efficiency. Superheat the steam. Again, another way to boost it up. So you take it up and you have more area under the curve. But most people got the correct answer, which was add efficiencies to the turbine and compressor. So if we put efficiency numbers in turbine compressor, obviously they're not adiabatic or isentropic anymore. They're probably adiabatic, but not isentropic, and therefore you get some inefficiencies. So here you have it. So that's the answer. Please review Rankine cycle. We are done with Rankine cycle. We've only spent 2 lectures on it, and you've done 2 homeworks on it. It's going to be the same deal with the gas power cycles. Gas power cycles, we might do 2.5 lectures on that, but really, I really want to get the refrigeration cycle. So the best I can do is to take you through Otto cycle today, and then try to do Brayton cycle on for Wednesday's lecture. So that's what we're going to do. It's not ideal, but we'll get you as far as we can with the gas power cycles, and hopefully you can understand it. If you go back, and nice thing about these lectures is you can just go back and look at them over and over again if you like. And you have the slides as well posted on Canvas. Okay, so Chapter 9. So the idea for Chapter 9 is that we're conducting air standard cycle analysis of internal combustion engines, Otto and Brayton. Those are the 2 air standard cycles we're going to look at. We're going to learn how to do PV and TS diagrams and evaluate property data at the principal states. We're going to apply energy and entropy apply balances, determine net output, thermal efficiency, and mean effective pressure. So those are things we're all going to do. Hopefully we'll get through all that stuff and you'll understand something. We already talked about a bit about this introduction stuff. There are ways to meet our national power needs, challenges related to declining availability of energy or fuels. These days, that doesn't seem that's happening. But effects of global climate change and certainly is a major concern that we have. Rapidly increasing demand for power owing to increased population. This is also something we've mentioned before. So we're dependent on coal, natural gas, and fuels, which are non-renewable. So petroleum is one here. Here, the electricity generation. But really, when it comes to transportation, petroleum is 99%, right? So that's what we're going to cover. We're going to cover engines. And so, cool. So these are just power generation stuff. Natural gas powered is the Brayton cycle. So this is an interesting cycle. This looks at all the different ways we use Rankine cycle. Brayton cycle is the cycle we're going to do for Wednesday's lecture, and that is a air standard cycle used in power generation. Okay. Vapor power cycles are the focus of Chapter 8, which we've already covered. In Chapter 9, gas turbine power systems and internal combustion engines are studied as thermodynamic cycles. you know, hold on. Okay, you know that the gas power cycle system in the gas turbine cycle is called the Brayton cycle, and then we talked a little bit about gas turbines a couple of lectures ago. So we're gonna do that stuff. Power cycle review. This should be total review for you. The first law of thermodynamics: work equals Q in minus Q out for a power cycle, work cycle, and thermal efficiency is equal to work over Q in. We don't need to belabor that. The second law of thermodynamics requires a thermal efficiency to be less than 100%, so obviously we can't have 100% thermal efficiency. It's limited by Carnot, which is the maximum thermal efficiency we can have. We improve thermodynamic performance of power cycles, accompanies a reduction of irreversibilities and losses. Of course, you want to come as close as possible to a reversible power cycle. That's what you want. Okay? Ideal cycles are formed from internally reversible processes used in Chapter 9 to further understanding reciprocal combustion engines and gas turbine systems. So closed systems involve expansion and compression work. So that's the piston and cylinder configuration that we're going to be talking about. In these applications, the following area interpretations apply. So for closed systems, we have the following. So the work and heat areas under the curve, right? Remember, work equals PdV for a closed system. And here you can see it's the area under the PV diagram. For the TS diagram, the area under the TS diagram gives you TDS, gives you the area under the curve, which is the heat. So the heat for our process is given in the TS diagram. So anyways, you can look at those things as examples of how we will be able to calculate power. So when inlet, when exit control volume analysis, you see that the work is equal to the VDP because that's the reversible work. The reversible work is equal to VDP for the reversible cycle, so that's kind of the area to the left. And TDS is the heat again for a given process for a control volume. These are important things to review. These are just review things that are useful for you, and you can have these slides. Now, in the gas power cycles, obviously it's called gas power cycle for a reason because we're talking about ideal gases. So we've talked about ideal gas law, which is here. These tables just summarize what's in the textbook and what we've already covered. So variable. So these are actually useful tables for you. I think you should just take a minute to consider these tables a little bit and look at the slides. So equations of state, PV equals RT, that's the ideal gas equation. This is the changes in delta U and delta H. Now, the definition is U2 minus U1 equals CV dt. And remember, when they put T here, it's not U times T, it's U of T, okay? I don't usually write it that way because I think it's confusing, but you get the idea. So likewise, H2 minus H1 equals Cp dt. Now, U2 minus U1 is equal to CV dt, so you can say CV T2 minus T1 if you consider constant specific heats. If you can't consider constant specific heats, which I will tell you in a test or an exam problem, at least I should, you can find these properties using the tables. So that's pretty straightforward. So you use the tables, or if I tell you constant specific heat, you find the specific heat and you solve for the temperature correctly. Okay? Here we go, changes in, so this is the TDS equation. You can see this is the change in entropy for an ideal gas. So variable specific heats, you have to use this S naught, which we find in the tables, and then this pressure correction term. Whereas in the case of a constant specific heats, you use these constant specific heat equations. Please review these equations. This is really important for an ideal gas, looking at these equations and understanding how to use them. I would really suggest making sure you know where to use these equations and when. Okay? That's really important. These are specific to ideal gases. Of course, the stuff we do for two-phase systems is a little different. Again, we've gone over these relationships. These relationships where you have T2 over T1. These are called the isentropic relationships. So this is where we have delta S equals 0. So if delta S for the process equals 0, you have this kind of analysis. So you can do T2 minus T2 over T1 equals P2 over P1 to the K minus 1 over K. And I'm actually going to do a quick example of this stuff for you when it comes to the next cycle. So don't get hung up on it, but if you have variable specific heats, you need to use this P2 over P1 equals PR2 over PR1, which we find in the tables for this is for isentropic process, and these are provided in the tables, which I've gone through and I've shown you, but I'm going to do an example of these too today. So I really have a lot to do, and hopefully I can get it all done, and we can really understand what's going on here. Okay? But I'm gonna explain these things to you, or use these things in the context of the Otto cycle, which is the next cycle we're going to talk about. Okay, some of my favorite things in the world: internal combustion engines, specifically reciprocating internal combustion engines. I have only now 40 minutes to tell you about my favorite subject of thermodynamics, which is of the entire class, which is sad to me, but in the interest of keeping you guys well versed in all the different areas of thermodynamics, I think it's valuable that we just stick to the small portion of time that we have available to do this, and then on Wednesday we'll talk about Brayton cycle, which admittedly is also kind of cool. Okay, so how do reciprocating internal combustion engines differ from vapor power plants? Well, first, they operate in gas; they don't do phase change, right? So that's obvious. You could answer that. But processes in the case of these internal combustion engines occur within a closed volume, closed system. The volume changes with a closed system, as opposed to a set of flowing system. It's like a bunch of control volumes. Okay, so it's just a different way to express the cycle. It starts and begins at the same state, thermodynamic state, so we don't have to worry about that. But it does have some key, key similarities. And differences. Okay, so first, before we get into pictures and drawing stuff and telling you about what it is, first let's talk about what the different kinds of reciprocating engines are. There are predominantly two types of combustion engines, internal combustion engines on the road and in society. These are the spark ignition engine and the compression ignition engine. The spark ignition engine is sort of what we'll be modeling today using the Otto cycle. In the spark ignition engine, a mixture of fuel and air is ignited by a spark plug, and so this is advantage for applications up to about 300 horsepower. Though there are much bigger spark ignition engines. In fact, some of the biggest engines are spark ignition engines, big natural gas engines. So I'm not really sure what they're talking about here. This is clearly not written by an internal combustion expert. Okay, but you get the idea. You ignite it with a spark plug, okay? And people are kind of familiar with spark plugs. I don't know. Maybe you've seen spark plug before or whatever. The other type is a compression ignition engine. And air is compressed to high pressure and temperature first. So that happens in a spark ignition engine too. But you typically compress higher to higher pressure, and combustion just occurs naturally. So due to the high compression, you get the fuel and air mixture ignites by itself. And that spontaneous ignition is what we call compression ignition. So this type is preferred for high power applications when fuel economy is required. Fuel economy is always required. Again, these slides are silly. I should have gone through and edited these. We always look for high fuel economy, right? And we're going to learn something today, a little factoid, that will help you understand what this is all about. But typically we use diesels in heavy trucks and buses, locomotives. Typically diesel engines have a lot higher torque, meaning that they can handle things that like tractors that need to move slow but have lots of torque. Typically that's why we use diesel engines, but okay. It goes along very much with the fuel, which I'm not going to have time to talk about. So let's just get into the main thing here. The main variable that you're going to need to know is this thing R down here, okay, which is called the compression ratio. Oops, where are we at? So compression ratio is here. So the piston cylinder looks like this. This is a nicer picture than we've been drawing since in the class, but you have valves and spark plug and all this stuff. You have what's called the stroke, which is the amount of movement that the piston goes, and the bore, which is the diameter of the inside of the cylinder. Now the piston moves up and down, of course, and there's what's called top dead center and bottom dead center. The reason why it's dead is because there's a curve, so it's a sinusoid. So at the top of the sinusoid, the piston stays still for a very long time, relatively, and then accelerates as it moves. So that's why we call it dead. The reason why engines work so well is because the piston sits around at top dead center for a long time, allowing combustion to occur over a certain amount of time, which if you take my combustion class or the combustion class ME3331-S20-Lecture37, you'll learn all about combustion and why it takes time and can't happen instantaneously. However, we're going to learn that pretty much combustion happens instantaneously here, and it's going to be useful for us. Here, compression ratio is the thing we need to know, and that's the volume at bottom dead center divided by the volume at top dead center. It's essentially the max over the min volume. That's max over min. Yeah, that's easy. Okay, 4-stroke cycle. This is not that important from what we're talking about, but this is what happens in a real engine. You have a PV diagram, and you notice that this thing looks really curvy. Well, it's really curvy because this is what it looks like in real life, a real life PV diagram. And actually, this PV diagram looks a little bit too accentuated, but that's okay. So you have the compression stroke here, you have combustion happening, which is setting this thing higher, then you have the power stroke, and then you have an exhaust valve, and you have this other piece here, which is like when the air is coming in, I'm sorry, the exhaust is going out, and the air is coming into the cylinder, and you have some air exchange. So really, in a real-life internal combustion engine, it's like an open system for part of the time and a closed system for part of the time. So one part of the so for part of time, when from this part of the exhaust valve opens to the point where the intake valve closes, there's air and fuel and exhaust products coming in and out. But in this class, we're not going to care anything about that. Okay, we're going to assume this is a closed system. So the intake stroke is here, and then the intake valve closes, and then you have a compression stroke, which occurs here, and then you have combustion happening right here at this X. Typically in a spark ignition engine, obviously it comes from the spark plug, and then you have a combustion happening, and then you have what's called a power stroke, where the piston's expanding, so you're making power. So it's called an expansion, until the exhaust valve opens, and you have what's called blowdown, where all this gases come flushing out of the system, and this happens on a millisecond time scale, right? So the engine's going at 1500 to 4000 RPM, and this whole cycle occurs within on the order of a few milliseconds, over and over and over again. Okay. Smaller engines operate on a 2-stroke cycle, which doesn't have that breathing, but it still does. The air still has to go in and out. But we're not going to talk about that. What I want to talk about is, first we have to, where are we at here? Okay. Yeah, so first thing we have to talk about is what's called the mean effective pressure, and this is a new thing we're defining. MEP is the net work done from one cycle divided by the displacement volume. Now, the idea behind MEP is that it's essentially the equivalent to like the mean pressure you find in the cycle. But what it's really useful for is, since it normalizes the work that's done by the cycle over the displacement volume, which is like how big the thing is, we can understand whether an engine is at high load or low load independent of how big the engine is. So like if you say an engine is operating at 2000 kPa, 20 bar, that means the thing is operating at really high load. Meaning, but if it's operating at 4 kp, 4 bar or 400 kPa, then it's really not operating at a very high load. So all I'm saying is that this is a useful metric for understanding the scale, of the engine, and understanding the power is normalized to the size. Okay, so we're going to calculate MEP today. You may not get a sense of it, but that's what we're going to do. Okay. So simulating internal combustion engines. So detailed performance internal combustion engines require consideration of complexities, including combustion and reversibilities, heat transfer, work. I mean, there's all sorts of other stuff too. We calculate friction, and we calculate like the pressure, how much gas is coming in, and when does it close, and there's turbulence. And it's a very, very complex process, which has kept engineers like myself busy for over 100 years. Okay? It works great, but there's all sorts of things to learn about it. There are so many different aspects of physics going on inside the engine that it just keeps us busy, right? Combustion itself is a hugely complex process. The air motion and everything. It's a very interesting and complex subject, and one that has provided us lots and lots of opportunity for study. Okay, accurate analysis of reciprocating internal combustion engines usually requires a computer simulation. I'm an experimentalist, so my feeling is that analyses generally requires more experiments, but we'll leave that to other people to decide. Air standard cycles. So what we're going to do is we're going to assume that all of those complexities are thrown out the window. Okay? Throw all those complexities out the window. We're going to assume that the engine operates as a fixed, closed cycle within a piston cylinder where everything, there's no phase change, there's no change of properties, it's just air undergoing a process, okay? An air standard cycle analysis has the following elements. So it's a fixed amount of air modeled as an ideal gas. So we can, ideal gas relations are from that table we just saw. The combustion process is replaced by heat transfer from an external source. It's a magical heat transfer that just comes in at one time. It's a little bit not very accurate, but it actually is more accurate than you think. There's no intake and exhaust process, so this is all, as I said, completely closed. All processes are internally reversible, which of course is totally false. And an cold air cycle, specific heats are assumed constant. So if we say it's a cold air assumption, we assume that the specific heats are assumed constant, which in an engine, temperatures are varying from 300 Kelvin to 2000 Kelvin. I guarantee you that the specific heat's not constant, but sometimes we assume that just to make cycle analysis easier, and which I will explain to you. Okay, so here we go. Reciprocating internal combustion engines, there are 3 cycles that adhere to the air standard cycle. Actually, there are others too. There's the Stirling and a bunch of other ones. Okay, but we're going to worry about the Otto, diesel, and dual cycles. And in fact, we are only going to learn about the Otto cycle. I've grayed out the other 2. So if you're interested in diesel cycle or the dual cycle, let me know. I'd be happy to explain them to you anytime. I love talking about these things. But right now, I think all I'm going to give you is the Otto cycle. Heat addition at constant volume. Okay? That's what we're going to talk about. Okay? The air standard Otto cycle consists of 4 internally reversible processes in series. They all operate inside a piston cylinder, and they look like the following. 1 to 2 is an isentropic compression. Piston comes up. Okay? Piston comes up, isentropic compression. No heat loss, totally reversible. 2 to 3, volume stays constant, and there's a combustion process, but in fact, we model that as a heat addition process. So instantaneously, the volume's not changing, the piston's staying totally still, heat is put into the cycle, okay, into the cylinder. And that heat goes from 2 to 3. So constant volume. So the pressure goes up, of course, and the temperature goes up. And then from 3 to 4, you have an isentropic expansion. So now you've combusted, now the piston's moving down. The piston moves down, you've got work. You're doing some extra work. And then you have process 4 to 1, which is normally the exhaust process where the pressure is dumped. Well, in this case, instead of dumping the pressure, we're imagining there's some magical heat release process that's sucking the heat out of the piston, out of the cylinder, which is, it's an okay analysis, right? Because it works fine. So the Otto cycle compression ratio is given by the big volume over the small volume. So V1 over V2, or the same as V4 over V3, because they're constant volume processes. So you can take the ratio of either one. Okay, you get it? I hope so. I've gone kind of fast, but I want to get to an example problem at the end of this. So let's keep going. So ignoring kinetic and potential energy differences, the closed cycle analysis for the 4 processes, the Otto cycle, reduces to give the following. So per unit mass, little w equals U2 minus U1, and they equal U2 the change delta U for each cycle. Okay. Sometimes you have work, sometimes you have heat. The nice thing is, you have an isentropic expansion and compression. That means that there's no heat. And if you have a constant volume, it means PdV equals 0. So that means that you have work equals U2 minus U1 and Q equals U3 minus U2. Okay? Super simple. This is the simplest of all cycles. The thermal efficiency then is the net ratio of the work to heat added. Okay, so let me get rid of this. Yeah, I'm going to do something else. So let's just talk about this first, and then we'll... where's my example problem? Oh, there it is on slide 31. Oh, yeah. So this is what we're going to do. Okay, so one thing I can do is give you a little example of this. And there's a really cool relation that is not derived here in the book, but I'm going to derive for you anyhow. So what I'm going to do is I'm going to go here. Where's this? Okay, I'm going to go to my iPad here, and I'm going to start a new file. And I'm just going to make a note here. So I'm going to go auto cycle at constant CV. Okay, we're going to calculate the efficiency. So we know the efficiency is equal to 1 minus Q C minus Q over QH, right? TL over TH. So this is the same thing. Efficiency is, but this is if you do anything, right? So this is Q. I'm sorry. This is work of the cycle over QH, right? And if you do the math like we've done, so this is the same for all cycles, right? All cycles. All right. So in this case, QC is given by oops. So what did we have here? Just go back. So here we have so the total thing is oh, the way they did it here was a little different, but whatever. Okay, so the QC is given by U4 minus U1 because if you look at the cycle, Q41 is Q low QC, so it's U4 minus U1 divided by, and in this case it's U3 minus U2, which is QH, which is the heat coming in. That's the combustion process. So U3 minus U2. Okay, I'm going to write that down. Now go back to my notes here. And then, okay, so this is what we got. Beautiful, right? Now, what if you want to simplify this? Well, if you simplify this and assume constant specific heat, what we call the cold air assumption, this is CV, CV T4 minus T1 over CV T3 minus T2. Now, of course, these CVs, if you assume they're constant, of course, they drop out. And so you have efficiency of the Otto cycle. I'm just going to say, I'll just say eta Otto is equal to 1 minus T4 minus T1 over T3 minus T2. Now, this is also great. Measuring temperatures is not that easy to do, especially since the engine's moving so fast. You can't actually measure the temperature inside an engine. So you want to come up with a way to do it differently. But remember, if we assume that those couple of processes, T4 to T3, are isentropic, we have it's V3 over V4 to the gamma minus 1. And we also have the compression process, which is T1 over T2 is equal to V2 over V1 to the gamma minus 1. Remember, these are the isentropic relations. Okay, so these are the isentropic relations. So this is for expansion. This is for compression. Okay, so we have expansion and compression. Now, okay, so what we can do is we can start messing around. Volumes are something we know. We know volume, right? So what we can do is essentially make some messing around here. So we can take these equations and we can assume then that this is equal to the compression ratio is the same to the gamma minus 1. So that equals the same thing because the T4 over T3 equals T1 over T2 equals the compression ratio, 1 over the compression ratio to the gamma minus 1. And then what we can do is we can essentially make the following after a little bit of algebra, which we're not going to do. So V1 to the gamma minus 1 equals T3 minus T2 to the V2 to the gamma minus 1. Okay, and then all you got to do is you substitute those in. So T4 minus T1 over T3 minus T2 is equal to V2 over V1 to the gamma minus 1, which is equal to 1 over the compression ratio to the gamma minus 1. Oh, interesting. So we have this ratio here, which was what we had here up at the top. So that's kind of interesting. So what we can do is just pull this down and say that the efficiency of the Otto cycle then is equal to 1 minus, let's just, hold on. Let me just, hold on. Let me just move this up. Where's my little clipper? My little clipper here. Yeah, I was going to move it up here. Okay, I'll just move it right here. Okay. Um, 1 minus, that way keep it on the same page. 1 minus 1 over compression ratio to the gamma minus 1. Really interesting, right? Um, Essentially what this means is that we have a relationship between the efficiency and only two variables for the Otto cycle, for the ideal Otto cycle. The compression ratio and the gamma, which is the ratio of specific heats. The gamma for, oh man, I use gamma, not K. Oh man, sorry about that. I use gamma a lot. This is K. I've confused you entirely. So it's the same variable. I just, in some places they call it gamma. In this book they happen to call it K. So I gotta change it. Let's see, K. Oh man, I use it all over the place. Get rid of it. Get rid of it. Okay, so K, K, K. All right, here we go. I got it. All right, it's K, right? So I'm sorry. It's 1 over compression, 1 minus 1 over the compression ratio to the K minus 1. Okay? Now, two variables. Really interesting, right? So what I'm going to have you do for your homework is actually make a plot. For your next homework, make a plot of Otto cycle efficiency. Does not look like Otto, does it? Okay, Otto cycle efficiency is a function of compression ratio for air standard cycle, right? Because air has the same gamma. There's no changing gamma. So this is kind of an interesting factoid. All right. So really, what happens is the higher the compression ratio, the higher the ideal thermal efficiency of an Otto cycle, which is why engines are always trying to raise the compression ratio higher and higher in order to achieve higher and higher thermal efficiency and higher fuel economy. Okay. That's just an interesting aside. Let's go back to the lecture notes here. I have some time left to go through this and do an example. So this is generally how we express the thermal efficiency, but we'll go through an example. So since the air standard cycle is composed of internally reversible processes, we can interpret the area under the TS diagram as the heat per unit mass, blah, blah, blah. Okay, and the closed area is the heat. We kind of know that, right? This one's closed area is the work, then the PV diagram, the net work output. Okay, the air standard cycle. So the compression ratio is an important operating parameter for reciprocating internal combustion engines, which we've just discussed. Super important because it defines the basic thermal efficiency that you can achieve. The highest thermal efficiency you can achieve is determined by the compression ratio and the K. So increasing the compression ratio changes the cycle. You can see it graphically here, actually. So graphically, it's showing that you increase the compression ratio, you end up getting higher, more area under the curve. So Otto cycle thermal efficiency increases, the compression ratio increases. And I've just given you a simple relationship that's not in the slides that you can use to explain Otto cycle efficiency as a function of compression ratio. Okay, it's not just linear increase. It has a function that you can see. Okay, let's do an example in our remaining time to do air standards Otto cycle. Okay, here we go. So let me go to example 1 here. Okay. Let's see. Now, what we've got to do is we got to say, like, read the problem here first. At the beginning of the compression process of an air standard Otto cycle, P1 equals 1 bar, T1 equals 290, and V1 equals 400 cubic centimeters. The maximum temperature in the cycle is 2200 K, and the compression ratio is 8. So 8 is actually kind of a low compression ratio in real life, but it's fine. It's normal. And let's see, determine the heat addition, the net work, the thermal efficiency, and the mean effective pressure. Okay, these are pretty straightforward to do. Now, it does not say assume constant the cold air cycle. It does not assume that we assume that the whole thing is cold air from a properties perspective. So we cannot assume constant specific heats. All right, so we're not going to solve it that way. So first, we're just going to put our known in here. So known is that we have an Otto cycle. It's air standard. We have to find is the heat addition. So it's kilojoules. Oh, which means that we're going to have to find the work. So anyway, we're going to find the mass. We're going to find the mass. So they want this. So they want they want Q in. They want which is Q34. We'll just say Q34. B, you want network, so you want work net. You want C, the thermal efficiency. And then D, you want the mean effective pressure, call it MEP. Okay, this is what you're going to find. Assumptions. Okay, so assumptions, we're going to assume A, we're going to assume that it's an air standard cycle. Okay, cycle. So air standard cycle essentially assumes that you have internally reversible processes. We don't have to write it down. It's just air standard cycle. B, we cannot not assume CV equals constant. So it's a varying, oops, I didn't mean to cross that out. I meant to underline it. Not assume CV equals constant. Okay. Okay, I don't think we have to do anything. So it's close. We'll just say, I like to say closed system. Okay, so let's go here and do a diagram. In this case, we're going to do two diagrams. First we're going to make our thermodynamic system and draw our system here, which is a piston and cylinder, of course, like we've always drawn it, and that's all you really need to do. So you have a piston and cylinder. Label your system, and you have air in here, and it's totally it's totally insulated except for the port where you put heat in. So Q in and Q out comes in through a certain surface, and then you have a piston. Okay, looks like that. Okay, good. And then you also have some work, so you have some net work of the cycle coming out. Okay, then you have follows an Otto cycle, 1, 2, 3, 4, and which we can draw on a PV diagram. Typically, we draw Otto cycle in a PV diagram. We could draw it on a TS as well. And I showed you what it looks like on a TS diagram, but I like PV diagram for Otto cycle because that's pretty much how we see it. One thing that's nice about a PV diagram is that you can actually measure the pressure and the volume inside the cylinder. So we can actually have a measured pressure volume diagram. TS diagram, well, you can't measure S because S is not something you can measure. And T inside is really difficult to measure. So pressure is really easy and volume is easy. So you know what these are. So P1 looks like this. So that's what the Otto cycle looks like. So we start here at 1, 2. This is compression. So in this case, you've got work going in, and then you work out up here, 3 to 4. And this is expansion. We have 2 to 3. You have Q in, and here you have Q out. And you put some arrows in here. So this is heat addition from 2 to 3, and 3 to 4 is the work output, the expansion work. Okay, that's pretty much all you got to do. So PV diagram looks like that. All right, so let's do the analysis. We can put our states in here if we want. So we have so P1 equals 1 bar at 290. So P1 is, what is it? What is it? 1 bar and 290. So the P is 1 bar, and so T1. So we'll just go analysis. We'll go state 1. We'll go state by state. So T1 equals 300 K. P1 equals 1 bar. And do we have anything else? We have V1. Do we have the volume? Yeah, V1. So V1. So good thing we can calculate mass. 400 centimeters cubed. Do we calculate the mass yet? No, we don't. But if we want to calculate the different processes, we have to look in the table. So air table, and we need to get U. So U1 is equal to, I'm not going to look at the table. I'm assuming you guys know how to do that. 206.91 kilojoules per kilogram. And then we're going to use VR1 because we have an isentropic process, and we're going to use the VR. Makes things easier on us for an isentropic process. So VR1 equals 676.1. Okay, let's see, state 2. So state 2, what do we know? So we know isentropic compression. So we know VR2 over VR1 equals V2 over V1. And we know VR1 and we know the compression ratio. So V2 over V1 equals small over big, so 1 over 8. So then essentially what we're going to have is 676.1 divided by 8 is equal to the other volume, which is, let's see, VR2 is 2, where is it? I'm trying to get lost here. 84.5151. And then T2 then is, I'm looking this up in the table, then from table we have T2, looking at the V2, so looking at the VR2, so T2 then is equal to 1159K, which you're using interpolation. All right, so you have interpolation there. So 1159K, and then U2 is equal to 475.1 kilojoules per kilogram. Okay, and now we have state 3. Because as you know, we mostly need to know the only thing we need to know is the internal energies. Okay, state 3. So we know that T3 is given in the problem as 2200. So P, well, we don't need to even know P3. We don't. So we know that U is only a function of temperature, though, right? So U3 has to equal whatever it is in the table. So that's 1872.4. And then we can look up VR3 equal 2.012 from the table. Kilojoules per kilogram. Okay, and then the only left thing to do is state 4, and we use the same relationships for the VR4 over VR3 equals V4 over V3 for isentropic. Only for isentropic processes you can use this relationship, this handy relationship. So just put that, make sure that we know it's isentropic, okay? So this gets us, let's see, VR4 equals VR3 over V1 over V2. So V1 over V2 is 8, right? VR. So in this case, this is equal to 16.096. And therefore we get T4 equals 1159.3. Oops, what happened here? Why is that the same? No, because I looked this up wrong. Shoot, I looked in the wrong part of the solution here. So these are wrong. That's 1159. All right, let's get this right. So T2 is equal to 652. Okay, and U2 is equal to U2 is 4. Oh, I had that right. 475. I just copied this other one down. Wrong. I just copied this other one wrong. So it's 652K, and then this one here is 1159.3K, and U4, which is the last thing we need, is 897.3 kilojoules per kilogram. So this is from interpolation again in the table, okay, using this number. All right, so because VR is only a function of the temperature, so that's the nice thing. For an isentropic process, it's really easy to find. So now the next thing we're going to find the mass, because they want everything. They don't want things on mass specific basis. They want things on a overall basis. So let's see. Okay, M equals P1 V1 over RT1, and that's R for that's R for air. So we have 1 times 400, and we're going to do a unit conversion here to get that into meters cubed. 8.314 divided by 28.97 is, remember, that's the molecular weight, 290K. And then we're going to have to do, let's see. So we have bar, so we're going to have to go 10 to the 5th bar. No, 10 to the 5th pascals. Oops, it's 10 to the 2. So 10 to the 2 kPa per bar unit conversion. And then you got to do a 10 to the, what is it? There's 1,000 cubic centimeters in a cubic in a liter, and 1,000 liters. So it's 10 to this. So it's 1 times 10 to the 6 cc per meter cubed, right? So there's a 10 to the 6 in there. All right. So anyways, the mass comes out to be 4.81 times 10 to the -4 kilograms. Look, there's not much. I mean, a kilogram of air is kind of a lot, right? I mean, to have a kilogram of air, it's kind of a lot. Okay, so there's not much mass, which is about right, because it's about right. Okay, so now let's see. Therefore, we can find A. We can calculate now. We know that this is really easy. So Q23 is Q in, which is what we're trying to find, right? A is to find Q in. Q34. And this is Q34, which is, of course, U3 minus U2. Yeah, I didn't mean 3,4. I meant 2,3. What am I talking about here? All right, so let's get where was I up here? 3,4 is the expansion. 2,3, that's Q in. So Q in is also positive. Q3 is positive. So this is like this times the mass, which we need to know because that's little u. And then that's pretty easy because now we have everything. 4.81 times 10 to the -4th. How are we doing time wise? Okay, we're almost done. Times U3 minus U2. In this case, it's 11872 minus 475, and this is giving us Q in equals 0.6715 kilojoules. Okay, so B is to find the work, so that work cycle is equal to Q in minus Q out, right? So work cycle is equal to Q23 minus Q41. And then so this is equal to Q23, which we've already found, minus U4 minus U1 times mass. And so if we do that, we plug that number in as 0.6715 minus we'll do the scientific notation here, 4.81 times 10 to the -4th kilograms times U4 minus U1, which is 897 minus 207, just rounded, gives us 0.3397 kilojoules. Oh, so good. We have more work than we have work. Look like we have quite a bit of work, actually. So C then, if we want to find thermal efficiency, is equal to work of the cycle over Q in, which is equal to 0.3397 divided by 0.6715, which is equal to 50%. Well, it's actually 50.6%. That's pretty high. Okay, let's just do a quick thing. Well, first let me just put this here. So I'm going to put mean effective pressure, as we said, is the work of the cycle minus V1 minus V2, and we know that this is work of the cycle over V1 minus V2 over V1, and V2 is the smaller, so 1 over compression ratio, which is 8. So then we end up getting, if we just put this all in, we have 0.3397 divided by 400 times 1 minus 1 over 8. And this ends up being, I think we're good, right? Well, no. I'm just trying to think here. Do we have, no, this is, so we need to make sure we have a correction factor for the bar to everything. So we need, so that's kPa, so 10 to the third Newton meters a kilojoule, so that works out okay. And then, so yeah, the bar and everything works out okay. So let's get, so there's 10 to the 6 centimeter cubed per meter cubed. And this will get us, oh, and then we need to get bar, because kPa. So it's 1 bar over 10 to the 2 kPa, right? Correction there. So MEP then is equal to, if we just do all the numbers, 9.71 bar. 9 bar is a somewhat high load operation for an engine. 9 bar is like accelerating onto the highway for a small passenger car engine. Okay, now if we're going to assume cold air for constant specific heat, we can use our handy relation here in our last minute. Oh, I'm already out of time, but 1 over RC to the K minus 1. And if we assume K for air is 1.4, this is 1 minus 1 over 8 to the 1.4 minus 1, which is 0.4. So this is 1.4 for air. And then if we calculate this using constant specific heat, which I don't, of course, haven't done, so let me do it real quick on my phone, and I will show you what that turns out to be. It's not going to be the same because constant specific heat is less accurate. So I'd say the solution we just got was more accurate, but let's just do it. So 1 divided by 8 is 0.125, of course, and that to the 0.4 power, 0.4 equals 0.3. So I'll just subtract by 1 and take the negative of that. We end up getting 56.5%. So 56.5, oops, this is 50.6. There's a big difference there, right? So the variable specific heat value is giving you a less efficient cycle than the ideal Otto cycle with the constant specific heat. I don't know. That's kind of interesting to me. Certainly, the constant specific heat is more optimistic about what kind of thermal efficiency one can get for an Otto cycle. Okay, so yeah. So stay tuned for the homework, and hopefully you can practice this. If you have any questions about the air standard cycle, please let me know. Also, you can look in the homework and review these lecture video or the slides. So we will see you on Wednesday.